Hi everyone, thank you so much for joining us today. Welcome to our July webinar. This month we will be talking about how wireless remote monitoring can help surveyors, engineers, contractors and owners to manage construction risk. So before we begin, as always, I'm just going to run through some housekeeping notes. We will be having a short Q&A session at the end of the webinar, so please do feel free to put your questions into the little question box and we will answer them at the end. And just to let you know that this webinar will be recorded and sent out to everyone who is registered afterwards. So I'd now like to introduce you to our speaker today, Simon Brightwell. With nearly 4 decades of experience in the delivery and marketing of testing, site investigation, survey and monitoring, Simon has a broad range of experience in the construction and infrastructure sectors. So over to you, Simon.
Well, thank you for making me feel very old, Anna. And thank you, folks, for joining today's session. Hopefully it will be of interest. I think it's an important topic because construction activity is a major cause of disputes, delays, claims. Activities like demolition, piling, excavation can lead to damage and disruption that affects potentially the thing that's being built, but also neighboring properties and neighboring infrastructure. So I think it's an important topic, and it's one where monitoring can play a key role. I hope that in this session I can demonstrate to you how an effective monitoring program, whilst not completely removing construction risk, can help to detect problems sufficiently early to allow you to change working methods, to reduce, to manage the risks. I hope I can also convey some other advantages, such as how it can characterize movement patterns that are actually normal and acceptable, and that are actually not linked with construction work, and therefore helping construction teams to defend themselves against claims that are in fact unjustified by providing evidence. So construction is a risky activity. It is one of the things that that humans do, which inevitably involves a degree of risk. I think that's not going to be removed. We see that sort of risk manifested in projects of all scales. We see it in big civil engineering projects. There was a report just in recent weeks around the 2009 collapse of a station construction on the Cologne Metro back in 2009. That was pretty high up in terms of consequence. 2 people were killed. I think the final bill for damage resulting from it was over £1 billion, and it had enormous knock-on effects. I think something like 40 buildings, including a government records office, were affected. Most of them destroyed or had to be demolished afterwards. The report that was published certainly in the UK engineering press in recent weeks, in this extract from Ground Engineering magazine, included the findings of an expert group who'd looked at that incident, and amongst their findings you can see here the #1 bullet point. So their recommendations in terms of future were that independent structural geotechnical review is essential. It must include checking of the design and the supervision, and it must include monitoring of the execution of the work. So monitoring was concluded from that disaster as a way of mitigating the risk in the future. And it's not just on these really big civil projects that things can go wrong. People with much healthier bank balances than me are spending a lot of time and a lot of money enlarging their particularly London residential properties. They're building big basements, they're burrowing below their terraced houses and building cinemas and swimming pools and all manner of other fine recreational spaces underneath the buildings. And a number of these, quite a significant number of these projects have gone wrong, even in residential projects. The example here in the Guardian newspaper is one where it goes particularly wrong. because it brought down 2 adjacent houses. So again, monitoring is not going to stop that kind of rather foolish activity, but it could identify the problems early enough so that the work could be stopped and the measures could be taken. I think the argument for monitoring is not just about stopping things going wrong, it's also to encourage things going right. If you take the example of the use of the observational method in terms of construction, those unfamiliar, this involves a continuous cycle of design, construction, monitoring and review. It's particularly suitable for complex geotechnical conditions because it allows for modifications based on actual observed behavior rather than relying solely on initial predictions and modeling. But the approach is really only effective when it's supported by robust instrumentation and monitoring systems that can provide virtually real-time feedback, real-time data. It's got a pretty long record. It's been used successfully on projects going as far back as the Channel Tunnel between England and France. It's used extensively on the Boston Big Dig project in the US. It was used on Heathrow Terminal 5. And as you can see from the example here, it was used quite a lot on the Crossrail or Elizabeth Line railway built in London, opened recently. In just one of the many sites it was used in, in the Western Ticket Hall construction, a review concluded that it enabled an entire level of temporary support struts to be omitted, that it had saved over £700,000 and that it had reduced the program by 4 weeks. So the benefits of a real-time feedback loop allowed smarter construction and engineering practice and brought considerable cost and program benefits. So when it comes to monitoring, the toolkit of instrumentation and monitoring hardware is bulging. It's been gradually filling up over the last 100 years or so. It ranges from relatively, or in fact, very simple instruments such as a telltale crack monitoring device. We're pretty much all familiar with them. Temperature sensors and various other simple analog devices, ranging through to much more complex and capable automated devices like the automated motorized total station in the central picture. But the lists are long, both for structural and for geotechnical monitoring. Most of these techniques need a person on site to take a reading. So sampling tends to be relatively sparse or infrequent. Operational cost is relatively high. And the industry is therefore moving more towards automated monitoring options such as the AMTS. These provide precise data, absolute data from many, many points. They're widely accepted and they're therefore used extensively in the industry. However, they are expensive in terms of the hardware. They do need a fixed power supply. They do need a line of sight. They do have an annoying tendency to be stolen, and they're not necessarily the right tool for every site or putting onto every corner of every site. And that's why I think the sector, the industry, has looked more endearingly at wireless options, not necessarily as alternatives, but as complementary options. Now, wireless technology, for people who are unfamiliar with it, involves the use of many dispersed sensors. They're generally smart devices. They're often able to self-configure, to self-heal, to respond to site conditions, for example, increasing the sampling frequency if they detect something interesting. And like a lot of IoT kit, it's generally fairly cheap, simple hardware, simple to use, and it doesn't need a lot of maintenance over a long multi-year lifetime. So if we take a little tour around a typical construction site, we can see geotechnical data coming in from piezometers, inclinometers, extensometers, relaying that data to a cellular gateway. We can see temporary works like a crane base being monitored, the structure, the weather data being monitored from the tower crane. The props and the beams in the excavation being monitored for load, for strain, and tilt beams looking at movement across the excavation. We can see the retained wall in the background there being monitored with crack sensors, and the tunnel below the site being monitored for convergence monitoring to look at any changes in shape, any deformation caused by the excavation nearby. So that's a kind of whistle-stop tour around a construction site, and we can see just some of the sort of common applications that where you might use this wireless technology. So what happens after that? Well, there is a fairly common thread to the pattern of wireless data flow, whether it's collected from one of the two platforms that Sensive offer, one of which is a mesh system we call flat mesh. The one on the top left here, where you have a mesh of sensors, for example, tilt nodes, which relay data to each other and back to the cellular gateway, or whether you use a longer wavelength system, a point-to-point system, such as what we call GeoWAN, which uses the proprietary LoRaWAN communication network to provide long-range monitoring, many hundreds of sensors per gateway, but not quite with all the smart features and interactivity that you get with a flat mesh system. Regardless of that, both systems will send data via a cellular link or an Ethernet connection to a platform called Sensive IO that allows the user to interact with the data flow, to manage the data flow, and also to manage devices in the field, to change configurations, alerts, thresholds, and so on. It also gives a choice of what happens next, to whether that data simply goes to the default Sensive data visualization platform called Web Monitor that allows users to interact with or monitor the system health and to look at things like battery levels and so on, to visualize the data, to do some calculations, to look at graphs, to look at patterns over time, and to manage alert thresholds and who gets those alerts and so on. Alternatively, from Sensive IO, the data can be routed out to a third-party data platform so that it can be viewed with all that other data that you might have coming in from your site, from total stations, for example. So, in a nutshell, that's the overview of the platform, how it works, and I just really wanted to spend a little bit of time looking at some projects where users have found different ways to take advantage of this technology on some international projects ranging from big to small to medium. The first of these is definitely in the big category. Sao Paulo, Brazil, population 12 million, growing extremely fast, a very clear need to improve public transit. The metro in Sao Paulo is being strategically developed, expanded. The Line 6 expansion involves 15 stations under construction, a railway of 24 kilometers length, and it is one of, if not the biggest projects going on in Latin America right now. It's had a somewhat checkered past. It's somewhat over schedule, over budget, maybe a familiar story for many big civils projects, but it has had a checkered past. In 2007, not on Line 6, but elsewhere on the metro construction project, there was a disastrous collapse. A sinkhole formed over an excavation. This resulted in the death of 7 people. It destroyed 90 buildings, and the constructors were fined $48 million. The contracted team, included Alstom, were banned from bidding for government contracts in Brazil for over 5 years. So those sort of consequences are very much in the to be avoided category. Moving Moving forward, 2022, problems hadn't completely gone away. There was a relatively a smaller collapse, which had not the same level of consequence, but it did damage an expressway next to one of the shafts after ground gave way to the side of the shaft. So I think if we look at the site, and there's some rather funky drone footage here, which illustrates just how congested, how complex, how complicated this project is in terms of the shafts and the station boxes being built alongside high-rise buildings, alongside busy highways, roads, bridges, very, very demanding civil engineering construction conditions. And obviously, with that history of collapses that have taken place in the past, there is a very, very clear need to tread carefully going forward. So there is a very robust monitoring program in place. It comprises a combined approach with a lot of geodetic instruments out there, in partnership with a lot of wireless systems. So you can see in the pictures here, you've got a AMTS looking at prisms on existing buildings in the zone of influence. We've got extensometers and inclinometers in use. There's obviously piezometers and all the other sort of geotechnical borehole logging that you'd expect from a site like this. And then below the ground, the newly constructed tunnels are being monitored carefully, and you can see here some Sensive optical displacement sensors set out in an array to monitor convergence, and these are set out at I think roughly 20 centers these arrays through the tunnel to look at any deformation, to sense that's happening, particularly and that extends beyond the tunnels to existing tunnels. The new metro lines are going within a few meters of existing tunnels, so they're being monitored. The shafts are being monitored with tilt sensors and optical displacement sensors. The bridges are being monitored, and the existing buildings in the vicinity are being monitored. And you can see here some of that sort of activity happening here, and some pigeons who are seemingly not impressed with the magnificent technology that's just being put in place there. So moving from Brazil to central London, this is another tunneling project. It may not look like it here, but this is Regent's Crescent, a grade 1 listed building in central London, built in the 1820s. It suffered bomb damage in the Second World War and was rebuilt. And a scheme was in place a few years ago to demolish the existing structures whilst retaining the listed protected facade at the front, and to expand the accommodation behind that frontage. It involved excavation of new basements, quite extensive new basements, which would be very close to London Underground tunnels, 2 sets of tunnels. Users here were an expert company, Murphy Geospatial, London-based monitoring company, survey and monitoring company, and they used a combination of technologies to do a fantastic job on this project of helping to manage what were really quite significant challenges. Those challenges become clear if you see the proximity between the proposed foundations of the buildings and the existing tunnels. So very, very close, within less than a meter, I believe, the foundations were going to be of the existing tunnels here. And on the right, the picture shows both prisms from a geodetic system, and next to them a series of tilt sensors looking at movement within those tunnels during the excavation and construction work. So it's a really complex site. It's a sensitive project for many different reasons. The solution that was taken here involved multiple use of total stations used in a live demolition site, the close proximity to an existing construction plant, a lot of demolition work going on, and they used more than 250 flat mesh wireless tilt sensors in the Jubilee Line tunnels, as we just saw. They were connected to the surface with fiber optic cable to get the data out in that case, and a combination of monitoring in the adjacent Hammersmith and City Line tunnels. There was quite a lot of clever thinking in the background. Some completely new algorithms were developed to calculate deformation, heave, and settlement, both to model it and to look at the actual movement during the construction. And the whole thing couldn't really have happened without the real-time data that I was referring to earlier when I talked about the observational method being managed remotely and used to inform the construction team and the stakeholders, the local residents and the local highway planning authorities and London Underground, of course, that this extensive demolition, excavation and construction project wasn't going to cause harm to others, and particularly to the London Underground network. You can see here a sequence of readings presented where, if I look at on the left here, this chart shows movement of the northbound tunnel from the tilt sensor data, and it spans the period during which the existing buildings were demolished and the excavation of the new basement was made. So on the top left, you can see the blue zone where nothing has happened, no construction activity has occurred, and no movement has happened. And as we span across that 5-month period, we can see gradually it moves through the yellow and orange color scales to a red, and the northbound moved maybe 2 or 3 millimeters, and the southbound moved vertically upwards. It heaved over 4 millimeters, but that was considered within the predicted limits. It was considered to be a manageable level of movement, and because the data were coming in consistently and virtually real time, it was felt that was a managed process, and the work could proceed because people were able to get their finger on the pulse, as it were, based on these data. Interestingly, I think it was said after this project that nobody could think of any project that's taken place in London where anybody's been permitted to build so close to existing London Underground tunnels. That London Underground would never have allowed that without the access to this data, and it was only really possible that project could go ahead based on the data that this system provided. And the proof is in the pudding. There's the finished building. And there also is the new civil engineer tunneling award for instrumentation for the best project in 2021. So we were all rather proud of that, and it was a really good team that worked on it. So hopping over the North Sea to Germany, this is in Frankfurt, moving away from tunneling and going up rather than down into the ground. This is a project, again, fairly common kind of application for monitoring. It's monitoring the facade of a historic building where the main core has been removed and a large high-rise building is going to be built within the core of this facade. So a whole range of monitoring took place here, but I think you can understand the advantage of a wireless system here in the sense that it was possible to mount these small, robust sensors. You can see a tilt sensor at the top, one of these little devices, and a crack or a joint movement sensor spanning over this stone entablature. That's a difficult word. This stone joint to look at the movement across the joint. It's a pretty difficult spot to get to. You don't want to be going back there all the time. The batteries in this kit will last for months, for years, certainly throughout the construction project's lifetime. So the advantage is it's pretty quick to put it in there. you're going to get virtually real-time data, and you don't need to keep nipping back up a tower, a scaffold tower, or renting in expensive access kit to reach that point. Railways are particularly susceptible, for obvious reasons, to movement caused by adjacent construction activity. Track geometry is critical to safe, efficient running of a railway, and many projects around the world use this technology where there is excavation or piling or foundation or under track crossings planned in the vicinity of the railway. And the advantage, again, like the building in Frankfurt, is that you can nip in there quickly in an overnight possession. You can install it and leave the kit, and it will get a whole variety of data on parameters such as track cross level, track twist, and an indication of relative settlement due to activity. So that construction of the A14 viaduct took place over a period of I think probably between 1 and 2 years, the duration of this monitoring project. The kit could have stayed in place. Some users decide to leave it in place to take a more long-term monitoring role after the project, but in this case it was removed. It could be used elsewhere. So that's an example of monitoring of a railway where there's construction activity above the track. And a common, possibly a more common application is where activity is happening below the track. Under track crossings, things like pipe jacking are becoming increasingly common because they allow work to happen without stopping the trains. And this little animation, I think, portrays the benefits of this approach quite easily. Again, installing the sensors on track sleepers, the construction activity, the excavation is taking place. Relative indication of settlement here or changes in other track geometry parameters like twist can be monitored virtually real time as that activity is happening. Measures can be taken, the work could be slowed down, ground freezing could take place, grout could be injected, trains could be slowed down. So if somebody smart is looking at that data as it comes in, there's a whole range of different options that are opened up to mitigate the risk based on the monitoring data. And I think that's probably a fairly useful place to finish on this this brief little tour, because I think that's a fairly common set of advantages that run across the use of wireless monitoring in construction. So I think, well, I'd like to think that I've portrayed some of the advantages here, that it's a system that can provide virtually real-time, virtually continuous data, and how that can benefit construction teams, how it can provide automated alerts so that people will be made aware of a problem, that it doesn't need a line of sight, so that if construction equipment is being moved around a site that could obstruct a geodetic survey, that will not affect a wireless system. That because it's pretty quick and simple to install and doesn't need a lot of maintenance, that it's something that will save labor. It doesn't need wired power and comms, so there's a lot less hardware, a lot less things to damage around the site, a lot less scope for accidental damage. There's less scope for things to be stolen because they basically don't look very exciting, and they are entirely useless to somebody who would take them away. And I think that because you're not visiting site as much, you're reducing the exposure to the workforce in terms of safety. There are limitations. If you take the example of probably the most widely used wireless device, a tilt sensor, it's limited in terms of what it can do in the Z-axis in terms of vertical movement. It doesn't provide an absolute measure there. It does rely on rotational movement. So therefore, some of those calculations are relative or derived rather than absolute. And there is still very much a scope, I think, here to see it as a complementary tool to the techniques like total stations that can provide absolute measurement. There is still very much a scope to see these things used as a sensible partnership rather than as alternatives. So that pretty much rounds up what I wanted to cover today. I could talk for several hours on this topic, but I'm supposed to stick to 30 minutes, and I think that's pretty much wrapped it up. So over to you, Amna, to see if there's any questions.
Yeah, we've got a couple through. Let's have a look. So the first one is, how easy is it to move kit around a site as construction progresses, or to take it from one site and reuse it at another?
Yeah, that's a good point, actually. Yeah. If you take the example of the progression, monitoring the progression of a tunnel, quite a common application is to monitor movement of precast segment linings. And teams doing that quite often will monitor near the tunneling face, but as settlement and movement become minimal after the construction, they are simply taking those tilt nodes off where they're mounted and moving them forward within a matter of days of their first installation. As the TBM, tunnel boring machine, moves forward, the nodes are simply moved forward, jump into web monitor, change the configuration for the location details, and that can be done really pretty simply. And that approach, I think, is modeled, replicated elsewhere. Construction sites, tall buildings go upwards. If you're looking at monitoring areas of interest, then you can move the sensors up as the building progresses, or down as an excavation goes downwards. So it is relatively simple and involves a little bit of reconfiguration, obviously, as the location changes. But it is a strong point, I think, that the kit can be reused on that site, and it can be taken to another project after this project is finished.
Someone's asked, is this the same technology applied in mines to monitor bench and tunnel movement?
Yeah, it certainly can be used in both of those sort of applications, and we've got clients who've done that with our kit. So yeah, I think the answer is yes. Bench movement in tunnels or in mines, yeah, looking at the stability of those, if you're concerned about collapse or a rock fall or a landslide event, then the use of this technology has been used, particularly together with cameras, to identify problems. Particularly using the GeoWAN system underground, it has been used in underground mines to provide deformation monitoring, the same as in railway tunnels.
Okay. Let's see what else we've got. Oh, another one. So, can sensors from other manufacturers be used with a Sensive system?
Yeah, good point. I think increasingly people expect that multiple sensor types from multiple sensor manufacturers should be combined into one system. And if you take, for example, weather stations, we're never going to, Sensive are not going to be in the business of building a weather station when there's lots and lots of very good ones out on the shelf. So we developed the digital interface node so that we can take data inputs from all types of other sensors and other instruments that have a digital output and feed that data into the wireless platform with all the advantages I hopefully described, as in just the same as a Sensive tilt node, for example. Yeah, it is possible to do that. There was another element to that question.
No, it's just if the sensors from other manufacturers can be used with a sensor.
Yeah, sorry. The other thing, the point I was going to make, I think, the digital interface node is a device that allows us to take digital inputs, but obviously there are older technologies, millivolt sensors, for example, can take data from devices with a non-digital output. So yeah, there is a range of options there to take third-party data, third-party sensor data.
Okay. Another question is, what skill and knowledge is required for this niche?
Required for what, sorry, Anna?
They've just asked for this niche.
For this niche, fair enough.
Yeah.
Yeah, most people who use this kit are not specialists in wireless condition monitoring. They are a broad group of people. They will certainly include people with a survey background in many cases, but increasingly they are people like asset owners. Network Rail, for example, are one of the biggest users, and the people actually handling the kit, installing the kit, and routinely maintaining and handling the data are Network Rail's team of contractors. They are not geospatial survey, I&M specialists in any shape or form, many of them. Because it's an IoT technology, we've tried our very hardest to make sure that it's possible to be used by people without a huge amount of knowledge at the start, that they can use things like the Sensieve Academy, the online training program that's available, and the Sensieve support team for advice and help in terms of remote configuration and so on. So we've tried to make it as easy as possible for people without a huge level of specialist knowledge to install it. Some people do have that knowledge, but it's not essential.
Okay. I've got the last question here, and that is, what happens if one part of a Sensieve system is damaged by construction activity? Will the whole system fail?
Yeah, that sounds like somebody who's been on a construction site and they're knowing the record of people to drive bulldozers over things, or for people to knock sensors off the wall. Yeah, it does happen. And as robust as the kit is, sometimes there is damage. If it's a node, a sensor node that is damaged, then the system will continue to function, both in a flat mesh system and in a GeoWAN system. The loss of one node, provided there's sufficient capacity built into it, so provided we're not we're still within range of a gateway, the system will continue to function, just having lost data obviously from that one part of the network. But it is healthy to build in redundancy. For example, if it's a particularly important site, then put 2 gateways on there, because if one gateway fails, then you are going to be losing data. The gateway can harvest data typically for up to 30 days and store it on the unit, so that if the part of the system that has failed is the transmission from the gateway, for example, due to a problem with the cellular system, then you haven't lost that data, you've just lost access to it until you can download it. But yeah, in general, I'd say it's a strong point of this type of approach, is that it can suffer damage to individual elements without systematic failure.
Okay. I think that's it for all of the questions. Unless anything's coming through. No. Okay. Well, obviously, if anyone has any other questions, please feel free to email us at info@sensieve.com. We will be announcing our August webinar soon, so please keep an eye out for that. Just want to say thank you to Simon and everyone who joined us today. Have a great rest of your day. Thanks all.
Thank
Bye.
you.